Hi folks, Buckley here. We're going to work through this 3D vector problem that I introduced in class, and we sort of sketched out the steps that we might take to solve this problem. Basically what it is we've got a pole coming out of the ground, and then we've got two cables, and we're applying force in each of these cables, and the forces are different. So one cable that goes from A to B, we're applying 840 newtons, and the cable going from A to C, we're applying 420 newtons, and we're being asked to determine the vector sum of those two forces that are acting in those cables. This is a type of problem that'll be super useful later on in statics. We're going to see it again and again. Okay, so I'm going to start this problem just by kind of stating what we know. So we know that we've got the diagram as shown on the right, okay? And then just to be perfectly clear, I'm going to name my vectors. So R is the resultant. R is equal to force B plus force C, where force B is the force from A to B. It's 840 newtons in magnitude, and FC is the force from A to C. It's 420 newtons in magnitude. So what I'm being asked for here, right, is the magnitude of R, which I'm just going to call R. Okay, so what is the magnitude of this resultant force? So we had sketched out how the steps that we were going to go through to solve this. And for problems that are kind of complex like this is going to take us at least this page, probably another page as well. It's a good idea just to kind of sketch out maybe how you're going to tackle it. This is a good strategy, especially for exams, even homeworks, but particularly exams. If you run out of time, you can at least tell us where you were going, and we can give you some partial credit for that. So the steps that we're going to take are going to look as follows. The first step is I think we should figure out what the coordinates of all of these points are, right? So we're going to determine the vector positions of points A, B, and C from the diagram, right? So we can tell those straight off the diagram. We have all these labels for dimensions. We should be able to get those just fine. Second thing we're going to do is we are going to determine the path vector, or the position vector from A to B, position vector from A to C, and I'm going to be strategic and make sure it's going from A to B because that's the direction that this is pointed, right? So this vector here is going from A to B. So we're going to then calculate from the positions that we have here, we're going to calculate D AB, which is going to be equal to B minus A, and DAC, which is this guy from here to here, is going to be equal to C minus A. All right. Now, what I really want, and I need to get to, is I basically need to get to these forces in vector form, right? So these forces act along this cable, and I need to extract basically the pure position component, right? So the vector from A to B has both a magnitude that's going to be, I don't know, 5 something meters, whatever. Okay, I'm making that up. And it also has a direction. So I want to just look purely at the directional component, meaning I want to find the unit vector that's along that line. Okay, so that unit vector, I'm going to draw it on here so we know what I'm talking about. It's going to be called D hat AB. And over here I've got its associated D hat AC. Okay, so I'm going to take what I have from 2 and I'm going to convert DAB and DAC into unit vectors, right? So to do that, it's pretty simple. All I'm going to do to get D hat AB, right, I'm going to divide, I'm going to take the original vector, right, DAB, and I'm going to divide by the magnitude of that vector. And I'll use this symbol, this way of representing magnitude, right? Same for this. D hat AC is equal to DAC divided by the magnitude of that vector. So what I'm doing here, just to be clear on this step, is converting to unit vectors. So these vectors with the hats on them, right, have a dimension of one unit. Okay, now I'm ready to actually start working with the force vectors. So FB is going to be equal to 840 newtons in the direction of this unit vector, right? So I'm going to say that's equal to 840, which is known, d hat AB. Similarly, FC is equal to 420 newtons, d hat AC. Then as step 5, I'm going to do the vector sum. So I'm just going to write it like this. I'm going to write these two together. FB plus FC, so this is step 5, is going to be equal to R, right? That's what I'm doing up here. Okay, R is going to be equal to 840 d hat AB plus 420 d hat AC. And step 6, I'm just going to take the magnitude of R, and that'll be my answer. Okay? So more complex problem, right? I'm just showing you what all the steps are, and now I'm going to go through and we're going to execute it. Again, good practice for you guys as we get into more complicated problems in statics, to actually lay out your plan of action. That'll help keep you on track, okay? And this is the meat of the thinking here, right? This is the meat of the problem. Okay, so let's start working on this. I'm going to purposefully kind of move this guy over. And I'll save our steps in case we need to see them a little bit later. But I'm going to put this guy back. Okay. And let's start by determining what these, step 1 here, we're going to determine A, B, and C, right? Okay, so A is equal to, point A is right here, so 0 in X, 0 in Y, and 6 in C. 0I, 0J, positive 6 in K. B, this point right here, is going to be, let's see, positive in the X direction, negative in the Y direction, and we're going to be 0 in the Z direction, right? It sits in the XY plane. So B, I should get, let's see, 3I hat minus 2J hat plus 0K hat. C, this point here, I'm going to get positive X, positive Y, and again 0 in Z. So I get positive X, I'm coming this direction, that's 2 meters, 2I, positive Y, 3 meters coming this way, plus 3J, plus 0K. Okay. Now, step 2, I'm going to determine DAB and DAC. And then convert those, I'll go ahead and convert them into unit vectors right away. Okay, so I'll do 2 and 3 sort of together. Should I keep them separate? I'll keep them separate. Okay. So position vectors. DAB is going to be equal to point B minus point A. B minus A. Looking here, right, component by component, I can kind of see what this is going to be. 3 minus 0 is 3, 3I. Minus 2 minus 0 is minus 2J. 0 minus 6 is minus 6K hat. Let's just double check this. This is a good practice too. Does this vector make sense? So to go from point A to point B, I'm going in the positive X direction, positive 3I, the negative Y direction, negative 2J, and the negative Z direction. I'm coming down, right? So negative 6K. So that checks out. Okay, DAC, that's this guy. Dun, dun, dun. C minus A. Going back up here, 2 minus 0 is going to be 2. 3 minus 0 is going to be 3. 0 minus 6 is going to be minus 6. Let's check if this works out too. So to go from A to C, I'm going in the positive x direction, coming out, the positive y direction, and the negative k direction, the negative z. That works. Okay. So now I'm going to convert position vectors to their unit equivalents. To do that, I'm going to first need to calculate these magnitudes. So the magnitude of DAB is equal to the square root of 3 squared plus 2 squared, right? Plus minus 2 squared, the negative drops out, plus 2 squared plus 6 squared, right? 3 squared plus 2 squared plus 6 squared actually gives me an even 7. DAC I'm going to get square root of 2 squared plus 3 squared plus 6 squared, 2 squared plus 3 squared plus 6 squared. That's also going to give me 7. All right, so magnitudes of both of these are actually equal. Those are two equal lengths. And that makes sense, right? Because it's sort of like on a kind of reverse grid, 3, 2, 3, 2, right? Okay, so what I'm going to do now is I'm going to use this. Let me start with DAB. DAB hat is equal to 1/7, 1 over the magnitude, times DAB. So that's 3i minus 2j minus 6k. So that's going to give me, for this vector, 3/7 I hat minus 2/7 j hat minus 6/7 k hat. Cool. DAC, applying the same principles to calculate DAC hat, I would get 1/7. DAC is 2i plus 3j minus 6k. So that's going to give me 2/7 I plus 3/7 j minus 6/7 k. Okay. Fourth step. I'm ready to start pulling in the magnitudes of those forces. So I've calculated the pure direction, right? The directional component. I've isolated the directional component of this vector here, just to its unit vector, right? The force B is going to be this given magnitude times this direction. Okay, so I'm going to multiply, it's a scalar multiplication, multiply known magnitude, known force magnitude by unit vector, right, to get those force vectors. So FB is going to be the known magnitude here, which is 840 newtons. Drop the newton. 840 times D hat AB, which is this guy here, times 3/7 I hat minus 2/7 J hat minus 6/7 K hat, which is going to give me for FB, when I multiply it all the way through, that's going to give me 361.2 I hat minus 243.6 J hat minus 722.4 K hat. And with obviously a little bit of rounding there, okay? All right. FC is going to be the known magnitude 420 newtons times unit vector AC. So FC is equal to 420 times this unit vector, 2/7 I hat plus 3/7 J hat minus 6/7 K hat. For this guy, I get 121.8 I plus 180.6J minus 361.2K. Okay, step 5, I'm going to add these together. All right. R is equal to, now adding down here, right, R is going to be equal to 483 I hat, so adding these two components, minus 63.0 J hat, these components, minus 1083.6 K hat. Okay. That is in component form. I just wanted the magnitude, right? So I'm going to take magnitude of R is equal to the square root of each of these components squared, right? So I'm going to let you guys do that step, okay? But what I get for that is 1188 newtons. There we go. All right, so that's the problem in its full glory. I want you to really think about if there's any points here that are confusing, I want you to go back over that and practice it. I gave you a couple additional practice problems that are working with position vectors, turning them into unit vectors, and then applying those to a force. That's called force along a line. Okay? Getting that technique down is going to be super important. Thanks for your attention.